So often, based on physical considerations, we have some information about the function values and the values of the derivative of function at a specific number. And in these cases, Taylor polynomials can be a good choice to represent the function, especially over a short period of time or an interval that's close to the number where we have the information. So an example would be a rocket ship. Remember here, if we're looking at the height of the rocket or the position of the rocket, that's going to be the original function f of x. The velocity of the rocket would be the first derivative, f prime of x, and the acceleration would be the second derivative, f double prime of x. So suppose we know that a rocket is launched, and at time x equals 3, it has a height of 100 meters, a velocity of 50 meters per second, and an acceleration of 20 meters per second squared. And we are asked to find a second degree Taylor polynomial that approximates the position function of the rocket near x equals 3. So the important thing to recognize here is that the information we're given can be translated into function values. We can see that f of 3 is equal to 100, f prime of 3 is equal to 50, and f double prime of 3 is equal to 20. Now we can plug this derivative information into our formula for a Taylor polynomial. So I'm going to have f of 3 plus f prime of 3 times x minus 3 plus f double prime of 3 divided by 2 over x minus 3 squared. Now be careful. I'm making a mistake here at the moment that I need to fix. Don't just use x. Remember that you're going to be using x minus 3 as your thing next to the coefficients because you're centering this at x equals 3. So our final answer for this example would be t sub 2 of x is equal to 100 plus 50 times x minus 3 plus 10 times x minus 3 squared. Okay, so as a second example, let's suppose we have a biologist who's tracking the size of a population of bacteria B at time t and wants an approximation of the function b of t. She knows at 1 second that the size of the population is 24 bacteria. The bacteria are growing at a rate of approximately 30 bacteria per second, and the rate at which the bacteria are growing is increasing at a rate of approximately 90 bacteria per second. And here we're trying to find a second degree Taylor polynomial that could approximate b of t near t equals 1. So again, we need to recognize when the real world information we're given can be translated into information about a function and its derivatives. Here we're going to have that f of 1 is equal to 24 because that's the actual function value. The growth rate is going to be f prime of 1, so we'll have f prime of 1 equals 30. And the rate at which the rate is changing is going to be f double prime of 1. So we'll have f double prime of 1 is equal to 90. Now we take our formula for a Taylor polynomial and we plug in this information, and we will get that b of t, the approximation t sub 2 of t, is equal to 24 plus 30 times t minus 1 plus 90 over 2 times t minus 1 quantity squared. So that's how we could use Taylor polynomial approximations to give us a formula that approximates any function based on information we have. And often we do have this type of derivative information from measurements that are made about real-world processes. It's just important that we recognize that we're actually dealing with that derivative information. And of course, it's also important that we know the formula so that we can take that derivative information and translate it into a formula for a Taylor polynomial.